Welcome to this lesson on resonance and natural frequency vibration. Resonance is a fascinating phenomenon that occurs all around us, from musical instruments to bridges, and even in our everyday objects. In this lesson, we'll explore why objects vibrate strongly at certain frequencies and how this principle affects the world we live in. Let's begin with natural frequency. Natural frequency is the frequency at which an object naturally vibrates when it's disturbed. Think of it this way: when you pluck a guitar string or tap a wine glass, it vibrates at a specific rate. This rate is its natural frequency. Every object has its own unique natural frequency, which is determined by its physical properties like mass, stiffness, length, and the material it's made from. Several factors determine an object's natural frequency. First, mass. Objects with higher mass tend to vibrate at lower frequencies. Second, stiffness. Stiffer objects vibrate at higher frequencies. Third, length. Longer objects generally have lower natural frequencies. And finally, the material itself matters, as density and elasticity play crucial roles in determining how fast an object vibrates. Now let's talk about resonance. Resonance is the phenomenon where an object vibrates with maximum amplitude when it's driven at its natural frequency. In simpler terms, when you apply a force to an object at just the right frequency, matching its natural frequency, the object starts to vibrate much more dramatically. This dramatic increase in vibration amplitude is what we call resonance. The key condition for resonance is simple but powerful. The driving frequency must equal the natural frequency. When these two frequencies match perfectly, resonance occurs. This matching of frequencies is what causes the transfer of energy to be most efficient, resulting in those large amplitude vibrations we observe during resonance. During resonance, energy transfer happens in a very special way. When a driving force operates at the same frequency as an object's natural frequency, maximum energy transfer occurs. This efficient transfer of energy causes the vibrations to build up over time, resulting in increasingly large amplitudes. It's like pushing a swing at just the right moment in each cycle. The swing goes higher and higher with each push. Let's look at a practical example: musical instruments. When you pluck a guitar string, it vibrates at its natural frequency. The sound box of the guitar is designed to resonate at those same frequencies. This resonance amplifies the sound, making it much louder and richer. Without resonance, the guitar string alone would be barely audible. The same principle applies to all musical instruments, from violins to pianos to drums. Resonance isn't always beneficial. A famous example is the Tacoma Narrows Bridge collapse. In 1940, wind forces matched the bridge's natural frequency, causing violent oscillations. The energy kept building up through resonance until the bridge couldn't withstand the forces anymore, leading to its dramatic collapse. This shows us that resonance can be destructive when not properly accounted for in engineering design. Let's recap what we've learned. First, every object has a natural frequency determined by its physical properties. Second, resonance occurs when the driving frequency matches the natural frequency. Third, this matching produces maximum energy transfer and large amplitude vibrations. And finally, resonance can be either beneficial, as in musical instruments, or destructive, as in the case of bridges and buildings. Understanding resonance is crucial for engineers, musicians, and scientists alike.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.